Hello everyone. So today the topic is kinetics. Okay, reaction rates, order, and half-lives. You take a reaction, the rate of the reaction very important. Okay, so for the reactant you should put the minus sign. Okay, don't forget to put the minus sign. For the product, no need to put. So rate is nothing but the change of reactant concentration with respect to time. Okay, like that. If you the stoichiometric coefficient should be mentioned 1 by a like that. Okay. For B, these are all are equal, okay, minus 1 by B dB by dt equal to 1 by C dC by dt equal to 1 by D dd by dt. Okay, so this is how a rate of a reaction. Rate of the reaction, I think, but how the A changed with respect to time RB, RC, RD. Okay, experimentally rate is rate constant into concentration of reactor, summation of all the concentration in the experiment. Okay, so in the experiment the rate is different than the calculator rate. Okay, because some of the reactant may disappear in the original rate experimentally calculated rate equation. Okay, so here the pi means multiplication. Okay, so sigma means summation, pi means multiplication. Okay, I equal to 1 to n Ci gamma I. Gamma is the order of reactant with respect to reactant I. Ca is the concentration of reactant I. K is rate constant. Okay, so summation of all the summation of I gamma I equal to overall rate of reaction. Okay, so if you take a zero order reaction, usually rare. Okay, A gives products. Okay, so the rate is minus dA by dt equal to K. So this is the rate of zero order reaction because here there is no A. Okay, so the A power 0 equal to 1. Okay, that is zero order reaction. So the unit is very important. Here you see the unit of K is moles per liter per second. Okay, so the already told the unit should be equal in two sides. So in the left hand side there is concentration of A. The concentration nothing but moles per liter. Okay, moles per liter is concentration, and below there is dt. Okay, so moles per liter second. Okay, so the right hand should be also moles per liter per second. Okay, so then differentiating with respect to, if you differentiate with respect to, you take the dA into dA equal to minus k into dt. Okay, so it's slightly rearrange this equation. Differentiate with respect to A0 to A. So A0 is the initial concentration of A and uh, a concentration of A at time t. Okay, so here also time 0 to t. Okay, if you integrate this, you get A minus A0 equal to minus KT. Okay, so if you take the A0 into this side, you get A equal to minus KT plus A0. Okay, so this is the concentration of A. Okay, K is the rate constant. Okay, so you like the, if you plot this is like y equal to mx plus c formula. Okay, so y is equal to mx plus c. Okay, here the formula is A equal to minus KT plus A naught. A equal to minus KT plus A naught. Okay. The C is the A naught. Okay. The constant is A naught. Okay. The X is T. Okay. The X is T. So the slope is minus K. The slope is minus K. Okay. The Y is A. Okay. You plot the Y A and the X equal to T. Then you compare these two. Okay, so y equal to a, my mx plus c, m is equal to minus k, so the slope is negative. Okay, so when the time is when the t of is nothing but the concentration of a is half. Okay, the time needed to uh, reduce the initial concentration of reactant to half. Okay, if you 100 moles of reactant A is, then the how much time needed? Okay, 10 minutes or 20 minutes to become 50 moles, like that. Okay, so how should you calculate? If you take the reactant and put substitute A equal to A naught divided by 2, and minus K into T into T of, okay, plus A naught. Okay, so take this side, K into T of equal to A naught minus A naught by 2. Okay, then you got A naught by 2. A naught minus A naught by 2, so 1 minus half equal to half. Okay, like that. A naught minus A naught by 2 equal to 1 minus 1 half equal to half, like that. Or A naught minus A naught by 2 is equal to half. A naught by 2. We need T of, or T of equal to, so the K become below 2K. Okay, A naught divided by 2K. Okay, so here A naught divided by 2K. This is how you calculate T of. Okay, so I told for first order, so you should calculate the remaining part. Okay, T of equal to A naught divided by 2. Okay, so first order equal to A into product. Here the rate, so this is nothing but the rate. Okay, so rate equal to minus dA by dt equal to K into A. Okay, okay, here the A is 1. So the A power is 1. Okay, so that is, it is first order reaction. So if you do the calculation, you get A concentration A equal to A naught e to the power minus kt, and ln A equal to minus kt plus ln A naught. Okay, just to take ln both side. Okay, ln both side means ln A equal to ln A naught plus ln e power. So ln multiplication become addition. Okay, minus kt. Okay, so the ln you can take the power into front side. Okay, so then become it is ln A naught minus kt. Okay, so ln E is nothing but 1. Okay, so minus kt. Okay, so ln A equal to ln A naught minus kt. Okay, this is how the equations are come. Okay, these equation also come, how they come from, if you take the A below and dA divided by A and equal to, and take the dt that side and negative also that side. Okay, K into dt. Okay, the same like that. A is 0 equal to A, integrating with respect to, and here also t 0 to t. Okay, so dt means differentiating dt, you get a t, and 0 to t means you get minus kt. Okay, so here 1 by A is nothing but ln A. Okay, ln A. So substituting, the limit is A0 and A. So first A, ln A minus ln A naught. Okay, equal to K minus KT. So if you remember all this, ln A minus ln A naught equal to K minus KT. Okay, ln A minus ln A naught equal to minus KT. Okay, so the same formula. If you want A means take the A naught that side. So ln A equal to ln A naught minus kt. Okay, then take e power. Okay, so take all the e power ln is 1. Okay, so A equal to e power ln A naught equal to A naught into multiplication. Okay, so this become multiplication, so e power minus kt. Okay, this is how the equation comes from. So this is the basic calculation, the ln A, or this is come again and again in the for the subsequent calculation. Okay, so like that, y is equal to mx formula. So the slope is minus k. And this is intercept ln a naught. Okay. So for t of equal to, for first order, ln 2 divided by k or 0.693 divided by k. Okay. So for second order reaction, the a become a square. If you solve the equation, you get the answer. Slope here positive slope, and intercept is 1 by a naught. So like that, you can derive the t of equal to 1 by k a naught. Okay. For first order in each component, for a plus b means dA by rate equal to k into a into b. Okay. So first order with respect to a, first order with respect to b. Overall, it is a second order reaction. Okay. So then kt equal to 1 minus a naught. So if you solve the mathematics, you get the answer. The special case when the concentration of a naught and b naught are same. Okay, so both are equal to 10 mole like that. Then it is like a overall second order reaction. Okay, so you get the equation like second order reaction. When the concentration of a is very much higher than the b, so then you get a first order reaction. Okay, pseudo first order reaction, because the concentration of a is very much higher. So then only the b only going to product. So b, the concentration of b only determine the product formation. Okay, so it is like first order with respect to b. Okay, like before we saw a equal to a naught into e power minus kt, like that you got b equal to b naught e power minus k dash t. Okay, so it is are the special case. Okay. Okay, determining order of reaction. How to determine the order of reaction experimentally? Okay, getting the data first. Consider the reaction, measure the concentration, or for gas phase, measure pressure, measure time. So and then spectroscopically follow the reactant or product concentration. Okay, etc. The second method, analyze the data. First, you should collect the data. The second, analyze the data. Reaction with one reactant. Okay, A gives product. So plot the analyte. Okay, so plot concentration of A versus T, ln A versus T, 1 by A versus T. If you see the first order, you plot. This is here. This is for second order. Okay, so in the second order, you plot 1 by A versus T. You get a straight line. Okay. In the first order, you plot ln A with respect to temperature. You get a straight line. Okay. In the zero order, you plot a versus t, you get a straight line. Okay. From these plotting a versus t, if you got a straight line means it is zero order reaction. Okay. Like that, you can collect the data and plot the data, you get to the answer. Okay. How you get it? Like that, a versus t means zero order. Ln a versus t, you get straight line means it is first order. 1 by a versus t, you get a straight line means zero, first to second order. Okay. So find which gives a straight line. Okay. Then half-life method. Measure half-life. Measure T of versus A naught. Okay. So for first order, T of is directly proportional to concentration of A naught. For the second order, T of is directly proportional to concentration of A naught whole power minus 1. Otherwise, T of is directly proportional 1 by A naught. Okay. So like that, if you plot which gives you a straight line. Okay. So if you see the graph for T of, if you plot T of versus T, you get a straight line. Okay. Multiple lifetimes. Okay. T of is the reactant to become half. Okay. So T3 of is the reaction further going to half. Okay. Meaning the concentration of A is divided by initial concentration divided by 4. Okay. So first order means the T3 of should be the ratio 2 ln 2 divided by k, and T3 of divided by 2 equal to 2. So if you got the T3 of divided by T of equal to 2 means it is a first order. If it is 3 means it is a second order, like that. Okay. So if you calculate multiple lifetime, if you know that these lifetimes, you can determine which that is first order or second order, like that. Okay. Reaction with more than one reactant, A plus B plus C, gives product. Okay. Initial rate method. Okay. So initial, if you take concentration of A, okay, and determine the rate, okay, at a time t0, okay, then the rate is equal to K into A0 power alpha, B0 power beta, C0 power gamma. Okay. So for different concentration of A, take the concentration of A different, then determine the initial rate. Okay, for same T0. Okay, so now the rate constant is rate is proportional to K into the, now the A concentration depends on the different A concentration. So just different. First you take A concentration and measure the initial rate, then change the A only, the concentration of A only, then measure the rate constant. Okay. Using this, you can experimentally determine the order of the reaction. Okay. So like if you take the second initial concentration is double times the, okay, so half. Okay. So the second A concentration is A naught divided by 2. Okay. So half the initial first you take, so first if you take 50 kg means second you take 25 kg. Okay, like that. So then R naught divided by R equal to, the others are constant. Okay, so the B and the C are constant, so cancel out. Okay, only these two are here, it is 2. Okay, so A naught, so substitute A naught, so substitute for A naught equal to 2 A dash. So 2 means they cancel out, you get to 2. Means the alpha equal to 1. Okay, so if you get to root 2 means the ratio of rate, the 2 ratio, the rate ratio is root 2 means the alpha is half. Okay, when if you get the ratio is equal to 2 means it is, okay. Then if you get to 4 means alpha equal to 2. Okay. So here mistakes are the, here put 2 A naught, 2 A naught dash divided by A naught dash, then the A naught dash cancel out, you get 2 power alpha. Okay, you get 1 means alpha value should be 0. Okay, alpha value should be 0. Okay, 0 order reaction. Okay, then only 2 power 0 equal to 1. Okay, if you got 1 means the alpha should be 0. Okay, so that's why I confused. Okay, so if you got root 2 means the 2 power 1 by 2 equal to root 2. Okay, so alpha is 1 by 2. If you got 2 means the alpha equal to 1. 4 means alpha equal to 2, like that. Okay, just varying the initial concentration of A, you can determine the order with respect to A. Okay, then change the concentration of B. Okay, change the concentration of B. First you change the concentration of A to A naught dash, like that. Change the concentration of B, you can determine the beta. Okay, like if you change the concentration of G, you could determine the gamma, like that. You can determine the order of with respect to A, B and C. Okay, flooding or isolation. Okay, goal is to try to make problem look like a one reactant system. Okay, flooding is making the concentration of B and C or anything. Okay, so more concentration than the A naught. So that is meaning that the concentration of the initial concentration does not change very much because it is huge, more than the needed for reaction. Okay, so the initial concentration does not change, then the reaction looks like the initial concentration does not change. Okay, C is approximately equal to C naught. Okay, so that dA by dt equal to K dash into A alpha, because these are constant, does not change. Okay, so you can take the constant whole K dash. K dash means K into B naught power beta C naught power gamma. Okay, so because then the alpha only changing. Okay, A power alpha. The reaction then becomes pseudo alpha order. Okay, so if it is 0 means alpha 0 means zero order, 1 means pseudo first order, like that. Okay. So complex reaction and mechanism. A series of elementary steps that make up the reaction. Okay, if you take a reaction like that, A plus B plus 2C gives D plus E. The mechanism could be A and B joining to give a F plus C joining to give a G plus D, G plus joining then again join the C. You get now the F and G are intermediates. Okay, they may be formed and decomposed. Okay, so you cannot observe in the product. Okay, but it may be formed. Okay, so the molecularity is the number of molecules that come together to react in one elementary step. Okay, that is molecularity. Molecularity is different from order of the reaction. Okay, so order of the reaction is for to here the molecularity is for a single elementary step. Okay, number of molecules that come together. Here the molecularity is 2, A and B. Here also 2. These all molecularity is 2. Okay. Here for single elementary step reaction, molecularity equal to order. Okay. So A gives product means it is unimolecular reaction. A gives product second order. Okay. So then bimolecular reaction. So then AB bimolecular, ABC termolecular reaction. Okay. So molecularity is the number of molecules that need to collide and in one step form the product. One step form the product. That is the molecularity. Okay. So order of the reaction is for total order. It may be two step or like that. So you should know the difference between molecularity and order. Okay. So parallel reaction. Parallel reaction. If A is simultaneously consumed to form P and C. Okay. Then the rate of dA by dt is K1A plus K2A. Okay. So K1 is consuming rate of A to form B. K2 is consuming rate of A to form C. Okay, so the total rate is the adding 2, 3. Okay, so solving the equation, you get a concentration of A, concentration of B, and concentration of C. So the branching ratio, concentration of B by C equal to nothing but K1 by K2. Okay, A are reduced, then A, B, and C are formed. Okay. Parallel first and second order reaction. A gives B with respect to first order. A gives C with respect to second order. Then dA by dt rate equal to K1A plus K2A square. Okay. Then A is K1A naught divided by e power K1T. K1 plus K2A naught minus K2 A naught. Don't muck up these formulas. Okay. Derive using mathematics. Simply differentiating, simply integrating this equation, you get the relation. Okay, so don't forget. So do the mathematics, then only if you do it, then only you understand. Okay, if I explain, you forget. Okay. Limiting cases, when the K1 rate is very fast. Okay, what happens? So when the K1 is very fast means then the A is A naught into K power e power minus K1T. Okay, so the it is very slow, so the consuming of K2 is very small. Okay, so then the concentration of A only determined from the K1. Okay, so when the K2 is higher means you get a first order with respect to K1. When the K2 is very fast means you get a reaction with respect to second order with the K2. So you know this is like second order, this is like first order. You know the formulas. Okay, consecutive or series reaction. Okay, A gives B and B gives C. So that is K1 and K2 with respect. Okay, so dA by dt is nothing but K1A. dC by dt equal to K2B. dB by dt is something. Okay, so here K1A is formed B. So minus K2B is decomposed B. Okay, so that the concentration of B depends on K1 and K2. Okay, so then integrating this equation, you get to the relations. Okay, just integrating the equation with respect to 0 to time t and concentration A0 to A. Okay, do it yourself. So here the concentration of A is here decreased, the concentration of B increased, but that also consumed by C. Okay, so it is because it is consumed. So A B formed consumed by C. Okay, so T max is nothing but when the concentration of B is maximum. Okay, that is the T max. Concentration of B how when max K1 by K2 A naught e power minus K1 T max. Okay. So limiting gas when K1 equal to K2. So solve when K1 is greater than K2. What happens? When K1 is fast, here the K1 is fast means the B is formed instantaneously. So the K2 is the slow step. That is the rate determining step. Then you can only see the B to C. Okay, so this is like unimolecular reaction B to C. So B to C. So the A concentration depends on A naught e power minus K naught. B is depends on K2. Okay. Okay, so this is the reaction like unimolecular reaction B to C unimolecular reaction. That is the rate determining step because the K1 is very fast, so that the B is formed fastly, then consumed very slowly by the C. Okay, by forming C. Okay. Okay, when the K2 is faster means what happens? K2 faster means the when B formed as soon as it is consumed by K2. Okay, K2 rate constant. Then the reaction is simply the A to B. Okay, A to B is the rate determining step. Then A is A naught e power minus e K1 T. B is K1 divided by K2 A. C is A naught divided by minus A. Okay. Reversible reaction. Okay, so if you take A gives B and B gives K1 and B to A equal to K minus 1. The K equilibrium equal to B equilibrium divided by A equilibrium. If first order means rate of forward RF equal to K1A, rate of backward RB equal to K minus 1B. Okay. At equilibrium, the two rates are equal. So the K1A equilibrium equal to K minus 1B equilibrium. Then K equilibrium equal to K1 minus K1 divided by K minus 1. Okay. First order reversible reaction. For first order reversible reaction, TA by dt equal to K1A minus K1 minus K minus 1B. Then B is nothing but B naught plus A naught minus A, and dA by dt equal to, then substitute for B. Okay. At equilibrium, the dA by dt equal to 0. Okay. Because there is no change. Okay. At equilibrium, there is no change in the A with respect to time. Okay. So then the equilibrium concentration A is K minus 1 divided by K1 plus K minus 1. So just putting the here, if you put here, it just substitute it, this equal to 0 and A equal to A equilibrium, A into A equilibrium, and then you get the relation. Okay, simple mathematics. You do it, it is very interesting. Okay, so this also same. Okay, so the why we always try to reduce it like this form. Okay, or like in the linear form. The need is, if you plot a linear graph, then only you can extrapolate to you get a better slope, because you always get a point like the if you get a curved point, you cannot plot a, if you point like that, you cannot get a point like randomly. Okay, so you cannot put a curve like that. Okay, if you get a straight line means, if your formula means, you can easily plot a straight line with respect to the experimental points. Okay, that is very important. So that is why always converting to straight line, because if you got a random point like that, you cannot you cannot plot a curve. Okay, because you got in random points. If you plot a for a curved point, you cannot plot a curve. Okay, it is maximum error, but you can plot a straight line very easily. Okay, that is the concept. Okay, so this is the plotting. So you see the K equilibrium equal to K minus when the concentration less than the equilibrium concentration, it try to equilibrium, attain the equilibrium. More than means it also less try to equilibrium. Okay, that is the concept. So okay, higher order reaction A plus B, second order forward and first order backward. So dA by dt k equilibrium. After much calculation get ms, but simplify from the beginning. Okay, by flooding B concentration higher than the A and C, then K1 equal to K2 B naught approximately equal to K2 B. Okay, then dA by dt is nothing but K1A minus K1C. Okay, this is now a pseudo first order reaction in A. Look like same on A. Okay, measure K equal to K2 divided by K minus 1. K absorbed equal to K1 plus K minus 1 equal to K2 B naught plus K minus 1. By changing B naught over a few experiments can extract K2 and K minus 1. Okay, series reversible reaction. Okay, so it is a equilibrium reaction and it further goes to C. Okay, so then dA by dt equal to K1A minus K1 minus K minus 1B, dB by dt equal to K1A minus K1 minus 1B minus K2B. Okay, so you should mention all the possible way of forming and deforming. Okay, dC by dt is nothing but K2B. Okay, can solve this, but it is an even bigger mess than part B. After flooding an approximation, it is not going to do much for us. We need to find new approximation for more complicated mechanism. Okay, what are the approximation? Steady state and equilibrium approximation. First we saw the steady state approximation. Okay, steady state approximation nothing but B is the intermediate. Okay, so B is very small and changing very small. Okay, because as soon as B formed, it is converted back to A or converted back to C, converted into product C. Okay, so the change of B with respect to time is very small, so you can approximately equal to 0. Then the K2 plus K minus 1, it is deforming is greater than K1. Okay, B reaches a steady state concentration B steady state and remains there. Okay, then dB by dt is nothing but K1A minus K minus 1B steady state minus K2B steady state approximately equal to 0. Then take the negatives into positive and you take the below, you get this, and dA by dt equal to K1A minus K minus 1B steady state, and substitute for steady state formula. So substitute for this here, you get this. Then dC by dt equal to there also substitute for B steady state, you get the answer. Okay, look like A gives B. Okay, first order K dash equal to K1 K2 divided by K minus 1 plus K2. Necessary condition for use of steady state approximation. What is the necessary condition? Data must be taken after B has built up to a steady state value. So after B has built up to a steady state, data must be taken after B has built up. Okay, then only you should take the data. Then B must be small. Okay, so the decomposition, the formation is very smaller than the decomposition, because then only the intermediate concentration very small. Okay, when the formation, what happens when the K1 is higher means there is the build up, the concentration of intermediate build up. Okay, so the K2 and K minus 1 are decomposition of B. Okay, decomposition of B. K1 is the formation rate constant. Okay, the decomposition should be higher than the formation. Okay, then only the concentration of B is small. Okay, so that is the steady state approximation. We come to the equilibrium approximation. What is equilibrium approximation? Assume K2 is very less than K1, K minus 1 and K1. Okay, so equilibrium approximation is so K2 is very less than, meaning that that is the rate determining stuff. The equilibrium is very fast. Okay, then the equilibrium like that. So equilibrium is very fast. Then slowly it form the C. Okay, very small drop. Okay, so the A and B are equilibrium with each other. Then slowly form the C. Okay, C. Okay, this is very small. Okay, so that is the equilibrium approximation. So that is B gives to C. Okay, K2, it is the rate determining step. Then A and B quickly come into equilibrium. As soon as B come to C, they also quickly come to equilibrium because the K1 and K minus 1 are very fast. So the concentration of these two are always in equilibrium, okay, because it is very small, okay. Okay, like that K equilibrium equal to K1 divided by K minus 1 equal to B divided by A, okay. Then so we know this, and B equal to K1 divided by K minus 1 into A equal to K equilibrium into A. So that is the equilibrium approximation, okay. So approximately we B divided by A. So we approximate the concentration because the this is very small, so you can neglect this, okay. Only equilibrium there, okay. So you can, this is very small, so that you can neglect this, that you can easily put only the equilibrium concentration of B and A, okay. So that is the equilibrium approximation. So then you can derive the dc by dt equal to K2B. So B is nothing but K equilibrium into A, okay. So the K equilibrium into A, otherwise K1 divided by K minus 1 into K2 into A, okay. K equilibrium is nothing but K1 divided by K minus 1, okay. Okay, dc by dt equal to K1, K2, K minus 1 to A. Looks like A tends to C, okay, with the K dash. K dash is nothing but this, okay. Okay, in general, for a mechanism with multiple pre-equilibria, like that, it is general for if you multiple p, okay, A equilibrium with intermediate 1, intermediate 2, intermediate 3, intermediate 4, like that, then finally gives the B, okay. You can use this formula, okay, like that, Kn intermediate In and equal to Kn equal to summation of 1 to n Ki into A, okay. Adding all the rate constant of each for each intermediate step, adding, not adding, multiplying, okay. So pi means multiplying, okay. So Kn into A. So this is the general equation, okay. Example, apparent intermolecular reaction. So you don't need to muck up the formula, so the same formula you see here, this formula only, okay. Kn is nothing but the final step, okay. Here Kn is nothing but K2, okay. Kn is nothing but K2. K1 is the previous reaction, K1, okay. Okay, if you take a reaction I plus M, M is a rare gas molecule or the wall, okay. It may be a inert gas or a wall, okay. It interact with this wall, okay, to form I2 and M, okay. So the rate is K. So mechanism is I and I form a complex I2 star, and it is collide with the wall or collide with the gas M to form the I2, and the transfer, excess energy transfer to M star, the M star back to the M, okay. This is the mechanism, okay, where K2 and K minus 1 are greater than the K1, okay. So the formation of intermediate I2 star is very small than the decomposition. That is the steady state approximation, okay. So like that, whether whenever the intermediate concentration very small, or the decomposition rate constant, decomposition is rate is higher than the formation rate constant, then you can apply the steady state approximation. Whenever the equilibrium exists, you can apply the equilibrium approximation, okay. So using the steady state approximation, formation of I, formation of I think you know the d star I2 by dt. What are the reaction they formed? What are the reaction they decompose? Okay. What are the reaction they form means positive, decompose mean negative. Okay. So just slightly rearrange the equation, you get the relation. Then substitute with respect, substitute in the rate equation, you get the relation. Okay. Limiting case. Okay. Limiting case when K2 M is greater than K minus 1. At a higher pressure, what happens? K to M is higher. Okay, what is K to M? You see here. What is K2 here? You see K2 is the I2 star is combined with the wall. At high pressure, the all intermediate I2 collide with the M inert gas or wall to form I2. Okay, so that is at high pressure. So it is second order with respect to I2. Okay, simply I. Okay, when the low pressure, the K minus it is very small. So K minus 1 is high. Okay, what is K minus 1 here? You see K minus 1 is I2 back to initial I. Okay, so that is the K minus 1. Here for this reaction the rate may be different. Okay, gas decomposition, Lindemann mechanism. A gas gives product. Okay, what is the mechanism? A plus M is a rare gas. Okay, so A plus M to K1 A star plus M, then the A star gives the product. Okay, K2 product B. Okay, so then K1 is fast. Okay, K1 is fast. K minus is very fast. K2 is slow. Okay, so K1 is formed, K2 is very slow. Okay, so K2 is the formation of product. Okay, it is very small. Then the decomposition of product. Okay, so K2 and so intermediate. You should know the intermediate. Intermediate K for intermediate K2 is decomposition. K minus 1 also decomposition. Okay, so K1 is formation. Decomposition is higher means steady state approximation. So then dA by dt equal to this equal to 0. Then you can A star. Okay, so then substitute with respect to in the rate equation, you get the relation. Okay, simple mathematics. The limiting case at a high pressure. Okay, at a high pressure what happens? The K1 M is higher than the K2. Okay, K minus 1 is higher than the K2. Okay, K minus 1 is higher than the K2. Okay, so at a higher pressure, the A star is combined with the M, collide with M to back to form the initial A. Okay, at high pressure. Okay, not forming the product. Okay, because at high pressure the A star and M are very close to each other, so they collide with each other to form the initial A and M. Okay, so that is what happens at a high pressure. The rate become K infinity A first order. So at low pressure there is no M nearby. Okay, so the reverse happens at a low pressure. Okay, complex reactions and mechanism. Okay, chain reaction, where a product from a step in the mechanism is a reactant for a previous step. Okay, so that is a chain reaction because the reaction feed its step. Okay, that is the reaction feed its step. Stationary or stable chain reaction. Okay, the concentration of reactive intermediate is constant in time or slowly decreasing. That is the stationary or stable chain reaction. Okay, for example, take acetaldehyde to decompose into methane and carbon monoxide. So experimental observation is small amounts of ether H2 also produced, and the rate of the reaction is directly proportional to the acetal concentration whole power 3 by 2. So these are the signs, signature, the chain reaction happened. So unwanted reactions are formed. The order is somewhat fractional. So then it is a signature of a chain reaction mechanism. Okay. What is the proposed mechanism? The K1 is CH3 CH4 is decomposed into CH3 dot plus CH4 dot. Okay, the propagation is the CH3 dot is combined with the CH3 CH4 in the rate K2 to form CH3 CO dot plus CH4. Otherwise, it decomposed into CH3 dot plus CO. The termination step is maybe the two CH3 combined together to form C2H6. The other side reactions are the CH3O dot is collide with the wall M to form the CO plus H dot plus M, or the H dot is collide with the aldehyde at K6 to form H2 and CH3 dot. The kinetic equation for each CH4 what are the step? The CH4 form, the CH4 formed in the K2. Okay, K2 CH3 dot plus CH4, like that. CH3 dot formed, decomposed, formed, decomposed. CH3 dot formed, decomposed. Okay. Okay, assumes a steady state approximation. Okay, intermediates are very small. Okay, so then assuming steady state approximation, these two are intermediate, approximate equal to 0. Then you find the relations, then substitute in the rate equation. Okay, same procedure. Okay, again and again. Okay, so chain length is the number of propagation step per initial step. Okay, the rate of product formation divided by rate of initial formation, that is determining the chain length. Okay, how much the rate of initial radical formation, how much the rate of product formation. This is the rate of initial radical formation, this is the rate of product formation. The relation between these two, the chain length. Okay, experimentally 300. Okay, non-stationary or unstable chain reaction. The propagation includes a branching step which increases the, when the propagation step includes a branching means it increases the concentration of reacting intermediate, then the explosion happens. Okay, for example, the combustion of hydrogen to form water, 2 hydrogen plus O2 form 2H2O. The initial step is the hydrogen cleaved into 2H2. The branching step is the H radical react with oxygen to form OH radical plus O, or the O react with H2 to form OH radical plus H dot. The propagation step is the OH radical react with H2O to form H radical and H2O. Um, then the H2 this reaction feed its step. The H2 react with O2 like that. This is like cyclic process. They happen and again and again. The termination step is hydrogen can collide with the wall with the rate K4T, or the hydrogen and oxygen and wall. The three all are again collide with each other to form H2O radical plus M. Okay, K5T. Okay, then the kinetic equation, derive the equation for dH, dO and d for the intermediate. Okay, then I assume steady state approximation. If steady state approximation fail means explosion, because this, what is steady state approximation? Intermediate concentration very small, that is the steady state approximation. When the intermediate concentration is not very small, it is increases means it become explosion. Okay, solve steady state approximation for O and OH and substitute in the rate equation, you get the answer. Okay, limiting cases, when the low pressure, when the low pressure mean wall collision dominate over branching. Okay, at low pressure it easily dominate with the collide with the branching. Okay, so here you saw the K1 and K5 and K4. K4 is greater than the K1 and K5. Here you see K4 is just to collide with the, at low pressure it easily find the wall nearby. Okay, so but it does not find here oxygen, or here what are the other reaction K5. So it is also impossible to find O and M together at low pressure. Meeting these three are impossible at low pressure. Meeting O2 are impossible, but meeting a wall is very much likely. Okay, because if you take H2 H radical, anyways it near a wall. Anyways it near the wall. You can easily collide wall. Okay, so that is at low pressure. It is this is higher than the colliding it. Okay, wall collision wall collision dominate over branching. Okay, so dominate over branching if branching doesn't happen means no explosion. Okay, at a medium pressure the branching is important. Okay, so then explosion happens. Okay, okay, at a high pressure also termination dominates. So at a high pressure the three are joining. Okay, so if we take at high pressure, the possibility of these three uh, combining is high probability. So this rate is higher. Okay, so at very high pressure, these three are combining, because at very high pressure, all reactant are nearby each other so that this reaction can proceed faster. Okay, that is at very high pressure. So at a high pressure, the termination dominates. K5T can't dominate. Okay, very high pressure, what happens? It react with further it react with H2O to become so at very high pressure this reaction formed. It is very fast. The product of this reaction is nothing but the OH dot. Okay, so it again react with H2 to form the OH. This is feeds the OH dot. Then the explosion happens because so this is take pressure versus temperature. So these temperature these are explosive region. These are stable reaction. Okay. Okay, branching chain reaction also occur in nuclear reaction. For example, in fission reaction of uranium 235, three neutrons are produced for each neutron that start the reaction. Okay, in a nuclear reactor, control rods that absorb the neutrons terminate the chain and moderate the reaction. Unless the operator is reckless and forget to insert the rod, in which case there is a meltdown of reactor core. There is don't forget to control rod. Okay, because the control rod is absorbing the extra radicals. Okay, here the neutrons. Okay, if you not absorb the neutron means it again collide with the uranium and explosion. Then uh, the core reaction core meltdown. Okay. Okay, temperature difference of rate constant. You Arrhenius law K equal to A power A into E power minus EA by RT. E is activation energy, A is pre-exponential factor. So if you take the ln KT versus temperature, A is the so slope is minus EA by R. It is what is happening? Slope intermediate intercept. Okay, this is intercept. Okay, okay. So if we take ln means ln K equal to ln A minus EA by RT. Okay, then this is Y. This is C. The m is with respect to temperature means the slope is minus EA by R. Okay, y is equal to mx plus c. Okay, now you see this is y, this is x, this is m minus EA by R, this is c. Okay, same formula. Okay, okay, A is unimolecular means A is the pre-exponential. It is normally 10 power 12 to 10 power 15 per second. Bimolecular means 10 power 11 liter per mole second. Okay, okay, the unit all very important. So physical interpretation of activation energy. If you take A plus B form C, the A and E are collide with form A activation complex A star and gives the product. Okay, so this is the A reactant, this is the complex, this is the product. So this is the activation energy needed to form the complex. Okay, when small A means weak temperature depression, fast reaction. Large EA means strong temperature depression, slow reaction. Okay, catalysis. Okay, a catalyst speed of the reaction but does not destroyed or used up in the process. Okay, if you take consider A and B in the equilibrium K1 K minus 1, let C be the catalyst. Okay, A plus C gives K2. Now the rate constant become K2 and K minus 2. Okay, now the K1 and K2 are very slow. After adding the catalyst, the K2 and K minus 2 are both very fast. Okay, so the mechanism is different. The what happens before when you don't add the catalyst, A become A star and gives the product. Okay, when adding the catalyst C, the AC activating complex formed, you get the B plus C. Okay, so reducing the activation energy of the complex. So reducing the energy of the activation complex, you reduce the activation energy. So this is for catalyzed reaction, this is for uncatalyzed reaction. So the equilibrium does not change though. Equilibrium does not alter. Only the rate is changed through lowering of EA. Okay, so the equilibrium does not change. The B equilibrium divided by B A equilibrium does not change. Okay, the equilibrium does not change. Only the rate is changed. Okay, when the catalyst added. Okay. So now for important enzyme catalyst. Okay, so enzyme or biological catalyst consisting of proteins that generally accelerate the reaction rates and so with exquisite specificity. That is, the chemical reaction involving one reaction goes much faster, but the other chemical reaction involving the same reactant or the same reaction per mode. So what is enzyme catalyst? So it is normally accelerate the reaction very much. Okay, and the specificity, it does not, it only work with the substrate A like that. It does not work with substrate B like that. Only it is specifically for specific substrate. That is the enzyme catalyst. Enzyme catalyst come into mind means the rate is increased than the specificity. Okay. Okay, the reaction in an enzymatic process is called a, the reactant in an enzymatic process is called substrate. Okay. For example, sucrose plus water and invertase. Invertase converted sucrose into glucose plus fructose. The lactase convert lactose to glucose plus galactose. Okay, so it is the milk sugar. Okay, so lactose intolerant means unable to produce the lactase. If your body is unable to produce the lactase means you cannot digest the milk sugar. Okay, you cannot digest the milk. Okay, that is mean. Then you need to take the medicine lact aid or other products. Okay, to form the lactase. In situ they form the lactase and hydrolyze the lactose to glucose galactose. Okay, fumarase to malate the fumarase. The for you see for every substrate you need a different enzymes. Okay, rate oscillated product specificity, substrate selectivity. Okay, invertase does not work on spalanda, which is chlorinated sucrose. Okay, so just chlorinating the sucrose does not invertase work. Okay, so here you say the invertase work in the sucrose. Just to replace one hydrogen with chlorine, the invertase does not work. You see how much the specificity. Okay, stereo specificity. So the most important mechanism, Michaelis-Menten mechanism. One mechanism that describes the behavior of many enzymes is known as the Michaelis-Menten mechanism. Here the E is enzyme concentration, S is substrate concentration, K1 forward, K minus 1 reverse. To form a ES is enzyme substrate complex. The complex decomposed into gives the enzyme back and gives the product P. Okay, so the rate constant is K2. So overall the substrate become product. Okay, that is the overall reaction. In the first step of the reaction mechanism, enzyme binds with the substrate, creating a Michaelis complex ES. The step is readily reversible. Okay, so in the second step, the substrate is converted to product and is released from the enzyme. Frequently this step is maybe considered irreversible because the concentration enzyme and product are very quite small. Okay, because enzyme is very small, so Kt is very large. Okay, the Michaelis complex E is generally present at very low concentration because enzyme concentration is also very small. Okay, treating ES is very steady state intermediate because it is very small. We can derive an expression. So derive steady state d ES divided by dt equal to, you see the ES formed in K1 E and S, K1 E and S decomposed into the K minus 1 minus K minus 1 ES and decomposed into K2 ES equal to 0. At this point, it is convenient to also replace E because it is often difficult to measure accurately. So the enzyme concentration is difficult to measure accurately because it is not the initial concentration of enzyme because when the reaction going enzyme initial enzyme also very small. So after it going into the reaction, you cannot mention the E means the enzyme concentration at when the reaction going on. Okay, so this is done by expressing the total enzyme concentration E naught, that is initial enzyme concentration, as a sum of free enzyme E and a enzyme plus bound substrate E plus. Okay, so total enzyme E equal to E plus ES. Okay, so if we want E means E0 minus ES. Okay, Although ES is very small, the approximation E, so here you see ES is very small, so you can neglect this. You cannot neglect like that, okay? Because E0 also very small, okay? So only when 10 lakh minus 1 means you can neglect the 1, okay? Because it is approximately equal to 999 is approximately equal to 1000, okay? So 999 is equal to approximately equal to 1000, okay? Like that. So, but E0 also very small, okay? So this is like 2 minus 1. So you cannot neglect the 1, okay? So because E0 is usually very small as well, substituting for E, one obtains. So substituting the equation for a enzyme substrate concentration, you get the relation. Okay. So then then in the rate equation for ES, substitute the relation, this equation. This is nothing but the Km, okay? This is nothing but a Km, Michaelis-Menten constant, K catalyst. So the K2 is normally when V stands for reaction velocity, okay? dP by dt is called V or reaction velocity. K2 has been replaced by K catalyst, and K1 K minus 1 plus K2 divided by K1 has been replaced by Km, Michaelis constant. One typically measure this initial value of rho, rate of appearance of P, at a series of initial values of substrate concentration, okay? Very different substrate concentration, you can uh, determine the rate constant. Two kinds of plots are convenient, okay? Here, okay, the initial slope is when the substrate concentration is very small, when here the initial, so this is the substrate. When the substrate concentration is very small, then you see the relation. When the substrate is very small means you can neglect the substrate concentration. So then the rate is nothing but K catalytes E0 divided by Km, okay? That is the initial slope, okay? When the substrate is equal to Km, what happens? Equal to Km means 2s, okay? S plus S means 2s, so the S is cancelled. K catalytic E naught divided by 2. That is when substrate V max divided by 2. What is V max? When the substrate concentration is very large. When substrate concentration very large, substrate concentration very large mean the Km become neglected. Then the S are cancel out. Then that is the maximum velocity. Okay, that is we called V max equal to K catalytic D E naught. K catalytic E naught is called maximum velocity. Okay, saturated because all enzyme are tied up with the enzyme substrate. Okay, you should know the plot, very much interesting. Okay, the initial slope must not confuse with the initial rate. Okay, don't confuse with the initial slope with the initial rate, because the initial slope is obtained by measuring the initial rate for several reaction mixture at the initial values of S concentration. Okay, so it does not come with a one initial concentration of S. It for taking different, the changing the S concentration, you get a different slope. Okay, then only you get the initial slope. Okay, this illustrates two important limits. When substrate concentration equal to Km, then the rate equal to K catalytic divided by Km E0 S. Okay, linear in S. Okay, linear with respect to substrate. When the substrate concentration very large, that is a V max equal to K catalytic into E naught. That is constant with respect to substrate. Okay, means it is independent of the substrate concentration, because here there is no substrate concentration. V max is the maximum reaction rate for a given quantity of enzyme E0. It is achieved at a saturating concentration of substrate at which every enzyme molecule is busy carrying out a reaction. Is Es equal to E plus P. Okay, and there are no free enzyme molecule waiting to find substrate. Okay, K catalytic is sometimes called to turnover number, because it is represent the rate at which each enzyme molecule produce products under this saturated condition. Okay, turnover number is nothing but number of enzyme molecule to maximum number of product formed per unit time. Okay, if you one enzyme, how much product formed? Okay, like that. That is the turnover number. Okay, so number of total concentration of enzyme is E naught. Okay, the maximum rate of the product formation is E max, K max. Okay, K max is nothing but K catalytic into E naught. So canceling E naught, you get the K catalytic. So the turnover number is nothing but the K catalytic. Okay, okay, I think you understand it. So line Weaver Burke plot. Okay, the so just taking the inverse. Okay, take the inverse of the reaction. Okay, taking the inverse and you separate the equation. So this is y and x is 1 by s. The slope is km k catalytic E naught. Then this is the intercept. So this is the intercept 1 by k catalytic E naught equal to 1 by v max. Okay, that is the intercept. So here you got a straight line. It is useful because it is linear with respect to 1 by s. Okay, so that is the it is very useful, linear with respect to 1 by substrate concentration. Okay, so how these come from minus 1 by k naught. Okay, so if you take in this point y is 0. Okay, so y is 0. Okay, so y is nothing but this 1 by that is 0. Okay, so then take this k catalytic inert into that side. Okay, minus 1 by k catalytic into E naught. Okay, k catalytic into E naught. Okay, then 1 by substrate, we want the 1 by substrate. Okay, so take these k catalytic E naught divided by km this side. Okay, the below become above, so below become above. Okay, minus 1 by k catalytic into E naught into, so these told become this side negative and this only there. So then the below become above k catalytic into E naught divided by km. Okay, if you cancel these two, you get to minus 1 by k. Okay, so you now you understand the difficulty of doing the mathematics. Okay, the mathematics very simple, but doing in the slide is very hard. Okay, that's why I skip the all mathematics steps. Okay, I think you understand. Notice this plot is, it is possible to apply in km and vmax without measuring E naught. Okay, here you can measure the km divided by vmax without needing enzyme concentration. Okay, you just need the substrate concentration and rate. Okay, plotting these two only, you get the slope. From that you can measure the km by v. However, in order to know the k catalytic, you know the vmax divided by E naught. Okay, one need an accurate measurement of E naught. To find accurate values of slope and intercept, it is necessary to sample a wide range of values spaced roughly equally in 1 by s. One usually set up reaction with value of initial substrate concentration and measure the initial rate for each to obtain the data for this plot. So you should take different values of 1 by s and plot with respect to rate. Then only you got the slope. Okay, accurate slope. So I think you understand. Okay, thank you so much. Revise the book at King's like that or any other physical chemistry book. You understand better. So it is just a overview. If you try, if you read today, you can understand better. Okay, thank you so much.